One of the most astounding, and perhaps the most astounding, bits of information passed to us during Tesla's AI Day is that our Tesla cars, assuming we're driving the beta, soon I hope, soon, are not only planning our own trajectories, but are doing that for all of the other important agents in the scene. In other words, they're identifying objects. This is a car, this is a truck, this is a person on a bicycle, etc., etc. They're understanding what those objects might do. This car is parked on the side of the road. This car is moving towards me on the other side of the road. This person on a bike is indicating a left-hand turn from the right-hand lane. And then it's path planning for all of these other agents in the scene. And then our ego car plans the optimal route based on all of this planning. You know what else does this? Human beings. You know what we are? We're conscious. Is your Tesla conscious, or will it be soon? I'm not talking metaphorically here, I'm being dead serious. Will we have to consider our Teslas conscious in the near future? And what are the implications of this? Let's find out. For those of you interested in investing, check out Webull, an amazing platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Hey y'all, it's Dr. Know-It-All. So I want to start by giving credit to Stephen Mark Ryan at Solving the Money Problem for kind of inspiring this. I had things tickling at the back of my brain, and this little clip at the end of a recent video of his sort of crystallized all of that. So I'll play that for you.
And in solving full self-driving, Tesla will have done most of the heavy lifting and built the foundation for solving the most important artificial intelligence challenge of our time: vision, and more importantly, perception, planning, and taking suitable action. This applies far more broadly than just full self-driving vehicles.
I agree with Stephen. AI Day was Tesla telling us that they are an AI company and they expect to solve the hardest problems on the AI front. And frankly, what is harder to solve than artificial general intelligence? But before we speculate, let's get the facts of the case by taking a look at what Tesla itself had to say on August 19th. If you're only interested in the speculation part, I'll put a break in the timeline so you can just skip ahead to that. But I think all of this stuff is worthwhile, and it's worth kind of like setting up the foundation for it so that you understand when we start talking about, I guess this is not really future speculation, this is more of a philosophical speculation that I'll be talking about later. But anyway, I think all of this information by itself is quite useful in its own right, and I think that's very worth watching, but also it sets up the whole philosophical discussion that happens later. And by the way, I think this shirt is very appropriate. This is in our merch store, "All input is error," which is a quote from Elon Musk, and I think this is really appropriate for today since we're talking about planning. So anyway, this part of the presentation was given by Ashok Elluswamy, who's Tesla's director of autopilot software. As this image shows, basically the goal of Tesla's planning software is to get from point A to point B, right? So you got to get from where you are to somewhere else, while at the same time maximizing the safety, the comfort, and the efficiency of the passengers. And as it turns out, somewhat mind-blowingly, this not only involves planning your own path in your own car, but planning for everything and everyone else around you as best you can, of course.
The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was a pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city street driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving than the car has to respond to all of cut-ins and crossing vehicles and pedestrians doing funny things.
So as you can see from this short clip, Tesla was able to do okay on the highway in 2019, which is kind of the Stone Ages at this point, right? But it could not do a good job in cities. Cities are too complex with too many variables to use the sort of old-fashioned planning system that they had. Why is planning for cities so much more difficult? Well, let's hear it from the source.
What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution.
So why is this such a problem? Well, as Ashok said, we have two issues. Number one, this is a non-convex space, which means you can solve part of the problem, but you can get stuck later. So imagine getting around parked cars, right? You solve getting around the first car, but then you get stuck trying to get around the second car. That's the sort of issue. Now, there are many, many other types of situations, but sort of metaphorically, the problem is that you don't have like an obvious downward descent. You have things with lumps in it, and you can get stuck in that lump if you're imagining, walking around or something like that. So that's basically the problem. So it's non-convex, which means you can get stuck in a local minimum. So the issue, of course, is that you have to solve the whole problem as well as you can, not just little pieces of it. This is very complex, and also you need a discrete search to try to solve this in a reasonably fast fashion. But then we get to the second issue, which is that this is high dimensional, and basically that just means that you're trying to plan ahead 10 to 15 seconds, which means storing a ton of data and processing a ton of variables. And if you haven't seen it yet, you should see my plan ahead video because that touches on all of this. And to solve problem number two, you need continuous function optimization. Well, whoopsie, these two goals require opposite solutions, right? One needs a discrete solution and the other one needs a continuous optimization solution. To solve this problem, Tesla basically used the best of each in a hybrid solution.
Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory.
So first, as Ashok says, we use vector space to represent the problem, which is super cool. You should watch my video on this. We're going to touch a lot on vector space in this episode, and it's really, really important. And if you haven't seen my previous video, you should watch that also. But basically, when people talk about vector space being kind of a cool thing that Tesla's doing, it's not. It's foundational to everything else that they're doing, including all of their planning solutions. So vector space representation of the problem was a foundational issue and something that they had to solve. And it's really cool that they were able to solve this, and now they can utilize this for things like planning and stuff. But anyway, Tesla's solution is to get an initial pass done with a very coarse discrete search in vector space, and then when you're close to the convex corridor you need to be in, you do a continuous optimization to smooth out the trajectory. And remember here that none of this requires the absolute best solution, just close enough. In other words, your car can make mistakes of centimeters without it being a problem. And that's, what is that? Perfection is the enemy of good enough, right? In driving, you need good enough. You don't need absolute perfection. So you don't need to waste cycles doing that. You just need to get close within a couple of centimeters of the right solution and you're good to go. So Ashok presents an example of making a double lane transition, which requires planning ahead, of course, because you need to make 2 lane changes. And note here that they use AppViz 3D, which is kind of cool.
So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one, it searches is lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes behind the other car, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan.
So note here that your Tesla is taking account of comfort and safety just like we humans do. Basically, the car's computer does thousands of searches in a very, very short time. It projects out to about 10 to 15 seconds. You can see the graphs to the right. And this is amazing that it's just cranking out these simulations internally as it comes up on a difficult maneuver. So again, here you're balancing safety and comfort and efficiency while you're trying to make the goal turn, just like a human being does. And note that in this image that the cyan line, which is the actual car's trajectory, matches very, very closely with the projected line, which was in white. That's pretty amazing stuff. But hey, any good driver not only plans their own future, but takes account of others in the scene. What will this car ahead of me do next? What will the car to the left that's speeding past me do next? What will the pedestrian who looks desperate to start crossing the street outside of a crosswalk area do next? All of these things are things that we humans take account of, at least if we're decent drivers.
When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side, but the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, okay, I have space here, this person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car.
So as Ashok says here, we're optimizing for the overall scene's traffic flow. That's incredible, right? We're basically planning for a scene rather than just planning for us alone. In the example he talks about, the yellow car in the image is obviously going slowly and is giving us the right of way, so we take it. But then the next car speeds into the scene. Well, what do? We should back off and let them go. But then that car stops and pulls over. So we change strategy and we move through. You can see from the red line in this image that Tesla guesses that this car is going to take precedence and try to drive through the scene. But the green indicates another future in which that car decides to pull over and let us through. And that's what the car actually does. So then the Tesla changes its mind and goes through the scene and goes past the parked cars and around the cars that are waiting for it. So as I'm sure anyone who's driven in this sort of scenario knows, these are intense and rapidly changing scenarios. And the car is reasoning about what the other drivers are thinking. In other words, like, that guy can't pull over, so I'll do it and let him pass. So think about that. The ego car is considering what it would do in the other car's position. You know, like, As Ashok says, to be a good driver, in other words, not too timid, autopilot has to be able to do this kind of planning. And I'm sure you can think of those awful drivers who don't take action and instead cause problems, right? They get too timid and they just wait and wait and wait. They clog up traffic and everything goes wrong. So you don't want to be that kind of driver. You want to be a good driver, which is what Tesla is using all of this planning ahead work for. And by the way, yes, if you're a timid driver on the road, I will judge you for that. One interesting side note here is that this is really only an issue for now when human beings and computers are sharing the road. Once all cars are full self-driving, this won't be an issue anymore, as they will likely be able to communicate with each other, or they will drive in extremely predictable manners, which will make it much easier for other cars to plan for them. But for the next several decades, full self-driving and humans are going to have to share the road, so it's going to be important for now. So anyway, after the course planning is done with the discrete search, we then move to continuous optimization to smooth out the trajectory of the car. In other words, we don't want it jerking us around or doing anything dangerous or stupid.
So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, here on the right side, the green plot. Has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it looked like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path.
So the corridor we see is the course path given by a discrete search, and then all alternatives within that are given a cost. In other words, safety, comfort, and efficiency all have to be maximized. On the left-hand side of this image, you can see 3 graphs that show how the costs are all being reduced to minimums for all 3 of these factors, which means you're reducing the risk, the time it takes, and the lack of comfort for the passengers. And on the right of the image, you can see it's also reducing lateral or sideways acceleration and jerk. And just a quick FYI, if you remember basic calculus, velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity, that feeling of being pushed back in your seat when you push the accelerator really hard. And then jerk is the derivative of acceleration. In other words, you don't want rapid changes in acceleration, like this, which is what makes you feel jerked around and possibly car sick at the end of a bad car ride. So the goal is to make those graphs on the right as smooth as possible and not, jaggy like this. And of course, all of this is planned for in milliseconds and then continuously updated, taking account of all relevant objects in a scene. This is really and truly astounding. And it's able to do all this calculation while spending compute time doing visual recognition, changing things to vector space, labeling objects, not colliding with something in the instant, et cetera, without leading to latency. It's incredible how much compute they're putting into a tiny little package. But hey, it's not enough to solve all of these problems. In more freeform problems, Tesla needs to be able to find optimal paths much more quickly with much less structure. In other words, crazy roundabouts, etc., that you can see in this image. So to demonstrate this, Ashok takes a toy problem, in other words, just a toy problem, and it's actually still really complicated. And that's a car trying to navigate a very crowded parking area to find a parking space.
So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The Ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So it is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search, and the heuristic here is the distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima, and it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic.
You can see that the older planning method needs 400,000 expansion nodes, basically trials, to get it to the parking space. That's not going to cut it. Providing a given path helps, but it still has like 22,000 expansions of the search to find the parking space. So what do we need to do? Well, basically we need to learn what the best parking heuristic is.
We train such a network for this simple parking problem. So here again, the same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting it stuck in any local minima. So this only takes 288 nodes and is several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic.
So a heuristic is a, quote, rule of thumb. In other words, it's something that just works because it does. It's not based on rigorous mathematics, if you want to be precise. But in a situation like this, what actually works best? Well, here's the beauty of neural networks. You can train a neural network to figure it out for you, which is pretty genius. By having a vector space representation of your scene, you can convert this problem from a messy 3D problem into a top-down 2D video game. And here you can see again why vector space representation is so important, right? It's able to make this conversion just brilliant. Anyway, then you just give this, quote, game a score. In other words, get to the parking space as fast as possible without risking other factors. And then you let the neural network figure out how to get the best possible score during the training. Interestingly, this training can even take account of driver interventions using real-world examples to help improve the score of this game. And by the way, note that this is all in training. We are training these neural networks. So this is all being done ahead of time, so the neural network just works when you need it to. And as you can see from the video and this image, it's super efficient. You can see this little hydra sort of branches sticking out of it as it moves along, but it's very, very localized searching, and it only uses 288 expansions. That's over a 1,000 time reduction in expansions. Like damn. And again, just to hammer this home, this is all enabled by Tesla Full Self-Driving living in vector space now. Essentially what we get is we get to see the global context, not just the local context. In a video game, we would call this cheating, right? You get to see the whole level at once, not just one part of it. And finally, let's take a quick look at the total architecture. So we start with the vision system, we convert this to vector space, again, super, super important. We then determine features in that space. We run a neural network-based planner for the scene. We feed that into explicit planning and control for the car, and then we output the steering and acceleration. All super easy to do, right? And now the moment you've been waiting for. It's speculation time. So let's consider a few things. Number one, the fact that Tesla Hardware 3, or Tesla Full Self-Driving Computer 1, as Elon has started calling it, is capable of doing this much calculation is frankly mind-melting. Remember, this is hardware that's been out for years in your car. Number two, I think from the things that I heard that Tesla is using both chips right now, not reserving one for redundancy. So I think under normal operations, there's two chips that are supposed to be redundant with each other, but I think they're being utilized for different functions under normal circumstances. There's probably a fallback mode. If one of them fails, it just goes into kind of a fail-safe mode and just gets off the road and stops. But I think they're actually trying to use both of these chips, simultaneously now, which makes sense because the odds of one of them breaking is pretty darn low. So what you could have is chip number 2 could be doing the path planning for other scene objects, while chip number 1 was doing your own path planning. Anyway, that's super cool use of the hardware that they have. Point number 3, they're using convex optimization at the end after all of the other steps. And by the way, I did an episode on this with SpaceX above if you're interested in that. And that's a pretty interesting intersection between the two companies, right? Which brings us to point number 4. Think about human beings and neural networks and convex optimization. The goal is to get good enough answers. In other words, the absolute minimum cost path planning might not be possible, or it might take hours or days to find this. And if you know about the traveling salesman problem, you know what I'm talking about. Basically, if you give a salesman multiple cities to go to, it becomes exponentially more difficult to find the exact right solution. But we don't need that. We just need to get close enough, right? We just need to get a close enough answer that's good enough for driving. And interestingly, if you look at this, the optimization happens at the end of the process after all of the other steps. And again, if you're interested in this, you can see some of my Explaining Andre videos plus the vector space video if you want to find out more about that particular aspect. So anyway, you have to identify objects first, then you have to determine likely paths from visual indications, in other words, yaw rate, velocity, and maybe other things like consistency of velocity, like, a drunk person or something like that. So all of this path planning is sort of the final step. It's basically the icing on the full self-driving cake. It's the step that goes from the immediate don't crash into something to the longer term 10 or 15 seconds of planning. And it fixes my issue with the current software's lack of planning. And again, you can see that video if you're interested. And of course, as Ashok said, Tesla is using the same neural networks to plan out likely paths for other agents in the scene. Again, the engineering prowess to do this in hardware and software is really astounding. And then it optimizes all of this to get, say, the 99% best path or a good enough solution to the problem. And of course, it takes account of things like driver comfort and the likelihood of being hit by others. One way to think about this would be like if you're in a valley in the mountains, right? So you've got the mountains, you've got a valley, and you want to walk down out of this valley, but then you get a complete fog in so you can't see a thing. So what you do is you walk around for a while until you identify the down direction. You take a couple of steps and then you walk around again until you find the new down direction, and you keep going, and eventually you're going to get to the valley floor. And then once you get to the valley floor, you keep going in a downward direction to get out of the mountains. So this obviously might not be the perfect path, right? It's not quite the shortest. It's not exactly the least amount of energy required to walk out, but it's very close and it's perfectly adequate for real life. And it'll save your butt if you're ever in the mountains in the fog. So there you go. So again, this is long-term planning on your Tesla's part, and it's taking account of other agents as agents in the scene. I suppose to continue and stretch this metaphor a bit, it would be like getting out of the mountains in the fog with big giant boulders in the way. So you have to plan ahead to get around those boulders as you start to see them as you approach them in the fog. And this brings us to the most speculative but highly interesting part of this video. Is your car, more accurately, will it be with the new software, conscious? I'm thinking of this question because of a book my doctor told me to read years ago, and thanks, Dr. Martin, you're the best. It's a book called Born to Run by Christopher McDougall. And by the way, I highly recommend the book if you want to read it. But anyway, in the book, McDougall posits that we humans have developed our higher order consciousness precisely because we evolved to be exhaustion hunters. In other words, if you think about us, we can't run very fast, but we can run for a really long time at a reasonably quick rate. And we can cooperate. So basically what we do is we get together and we exhaust prey by tiring it out and then going in for the kill. Or at least we did back in caveman days, not so much anymore. But that was the strategy of us killing things, way back in the day, at least to the best of our knowledge. But think about this for a second. This strategy is not really possible without an intimate understanding of other agents. In other words, we have to project intent onto other agents. One of them would be our co-hunters, right? We have to know what they want, but especially we have to project intent onto our prey. So obviously communication with our co-hunters requires some sort of language, and that's really cool. That's how, probably language developed, or at least that's one case for how language developed. But placing our minds into the minds of our prey requires quite the mental trick that McDougall says is the basis of consciousness. In other words, it's the idea of getting into the heads of other creatures and placing ourselves there. Now, of course, this is a philosophical argument more than anything else, so you don't need to necessarily agree with this 100%, but let's just take this as is for the moment and run with it, or maybe drive with it. So what does your Tesla do here? Well, it places itself in the minds of other agents in the scene as it's doing route planning. In other words, it's acting in a conscious manner by this definition, or at least some sort of proto-conscious manner. In other words, it's giving agency to other objects in the scene. It's an I-you relationship, according to philosopher Martin Buber, rather than an I-it relationship that gives no agency to other objects in the scene. They're just objects to be manipulated. And that, my friends, is consciousness, at least by one definition, a kind of functional definition of consciousness. Or at the least, it's the beginnings of consciousness by this definition. And now let's think about what Elon keeps saying over and over again. Solving full self-driving meaning solving a major part of real-world AI. And what can this be used for? Well, certainly not just driving, but Tesla bots and any other silicon entities that exist in the world. In other words, Elon has been telling us that Tesla is effectively working on solving AGI, or artificial general intelligence. Now, I have to admit that this was stunning news, and I've had to take some time to process this thought, as even to me it sounds kind of insane, but I think that's what's being telegraphed to us over and over again. And remember, Elon likes to tell us things, and he likes to do it in kind of a secretive sort of manner. In other words, like, I guess, hiding in plain sight sort of manner. And so I think here, at least by one definition, this functional definition, we're already at the dawning of consciousness in Tesla's driving, full self-driving, 9.x beta, and it's only supposed to get much more advanced with version 10, as Elon said. So yes, folks, not to sound like a crazy person, but I think that Tesla's under-the-radar goal here is to develop AGI. And yes, folks, I think that those of us driving full self beta 9 around are letting a brand new silicon-based proto-consciousness drive us around. That's totally crazy, right? Or is it? All right, I hope you found this episode fun and informative and a little mind-blowing, and I'm sure I'll hear in the comments about how you're arguing against me, or maybe people will agree with me. Who knows? Anyway, in any case, definitely like this video so other people can find it. And this is number 5. I've got one more video in the AI Day sequence to go, so definitely hit the bell notification icon if you want to find out about that one. As always, a huge shout out to my patrons on Patreon. Thank you all so much for your help, your support, the conversations. I love all of this stuff that's going on in the community, so thank you so much. And of course, if you're interested in joining, check out the link in the description. And if you're interested in some awesome merch, check out the link in the description. We've got the Tesla Bot t-shirt, which is super popular these days. Don't mess with Tesla. Lots of other t-shirts, tumblers, mugs, etc. So check out the link in the description and help the channel out. And for those of you interested in investing, check out Webull, an amazing platform platform for buying and selling stocks, and now cryptocurrencies like Bitcoin, Dogecoin, and others. Open an account and get a free stock valued at up to $200, and fund your account and get another free stock valued at up to $1,600. Check out the link in the description and help the channel at the same time. Thank you. And finally, don't forget that we are both Tesla and Amazon affiliates. If you look in the description, you can see how shopping for a Tesla, a solar roof, a Powerwall, or anything on Amazon helps out the channel. And as always, feel free to ask me questions in the comments or at my email address, which is drknowitallknows@gmail.com. Till next time, bye-bye.